So I'm going to introduce Ceres, which is the largest asteroid in the main belt and a candidate ocean world, or perhaps a candidate fossil ocean world, depending on your perspective. And what Julie wanted to do was to highlight some of the physical and chemical processes that we think are going on this small oceanic world, let's say, and how it might inform our discussions today. So I'll start with the description of Ceres. Ceres is about 1,000 kilometers across. It has a very low albedo, similar to the moon, low surface temperature and density that is consistent with a body that has a high water fraction. Estimate is somewhere in the range of 50% by volume water. And that makes this the most water-rich body in the solar system inward of Jupiter, inward of that zone. So that makes it a body of some interest. And there are pre-dawn models that predicted aqueous alteration in the large ocean, and of course the pre-dawn, which dawn is the mission that is currently orbiting Ceres, about to complete its final phases starting later this month. And of course, pre-spacecraft models often go in the trash bin of history. And we shall see. This slide here just shows, puts Ceres into a bit of context. Enceladus is a body we've been talking a lot about, the moon of Saturn. Pluto, and here's the moon for scale. Europa is about midway between these two bodies in size. So Ceres is substantial, but it's actually still quite a modest little body. We do have several lines of geophysical evidence that inform us about what the interior probably looks like. Of course, we don't have drill cores, so we don't really know with precision, but we have, it is an orbiting mission. It got within 200 or 300 kilometers of the surface and has been orbiting for close to 3 years now. So it's got a good gravity map of the surface, not quite as good as we have the moon, but still quite good, which indicates partial differentiation of the interior. It's not completely condensed into an iron core and water-rich crust. And there was a lot of speculation before we got there as to whether there would be a thick ice crust on the interior and in the exterior based on the shape and gravity density. But we have other lines of evidence. One is that the crater morphologies are not nearly as relaxed as we predicted before. If it had been a solid ice crust, the expectation was that almost all the craters, at least in the equatorial region, would have been completely relaxed due to viscous flow, and that's definitely not the case, which indicates that the crust is stiffer than we expected. I'm not sure where this comment comes from. Somebody might know about that, but the topography in terms of the overall shape, the degree of flattening of the body, which is a little bit flatter than expected, if I remember correctly. I might have the sign wrong on that. And also the spectrum of the topography in terms of how rugged the body is as a function of wavelength is also more consistent with the ice shell being much stronger than it would be if it was just pure water ice. So it indicates you have a rocky mantle and an outer layer of mixed ice, salts, and silicates, and possibly clathorites, giving you a density of about 1.25 or so in order to match the gravity data. So it's partially differentiated, which gives you an interesting mixture in the outer zones. And there's speculation about there being residual brines in the outer layers, which we'll talk to in the second half, I think. We do have multispectral coverage of the surface, all of which is leading us to the conclusion that there is a global extensive episode of hydrothermal alteration of the entire body, outer layers of the body anyway, given the fact that we have basically a homogeneous global composition dominated by ammoniated clays, serpentinites, carbonates, and of course a large fraction of spectrally neutral material as well thrown in, and outcrops in various locations, particularly in the floors of craters, and some of the ejected deposits. This is Okator crater, the famous bright spot feature, which is highlighted by sodium carbonates, ammoniated salts, which are only found in 2 other locations, hydrothermal deposits on Earth and the erupting jets and enceladus, which is again, a very strong indicator of hydrothermal alteration across the entire body. And there's an indication of organics in at least one location and possibly several other locations. This is a very old crater, several dozen kilometers across, which is an interesting find. It's not widely distributed; it's very localized, which is an interesting problem in and of itself, how it got to those locations. And finally, we do have elemental maps of the surface given to us by the gamma ray instrument on board. It's a very coarse map because of the nature of the collection device, but it does indicate that you have ice-free regolith in the equatorial region, which has a bulk composition similar to Ci and Cm chondrites, with an iron abundance that is somewhat lower than the average composition, and that could be consistent with sinking of metal-rich particles in an global ocean, depriving the surface of those iron particles. And with that, I'm going to transfer over to Mark.
Okay, can you hear me all right? Okay, so we know that Ceres surface is bearing materials of water rock alteration, products of water rock alteration. And the question is, how much of this alteration has taken place? The surface is very homogeneous, so we see these products everywhere. And there's a growing agreement now among people who look at how Ceres has changed over time with numerical models, that this alteration perhaps has taken place over a very long time and has been pervasive. So the figure you're seeing here on the left shows a cross-section of Ceres. So this is the center and this is the surface. And has the interior of Ceres be essentially unconsolidated. So the rock is thought to be very silty and fine-grained, such that you have a first layer of convection here and a second layer of convection here, but you never have this separation again between rock and ice. So as Paul mentioned, the surface being very strong, it's thought that there is still a significant fraction of rock mixed in, perhaps along with salts and clathrate hydrates. So all that makes for a setting where you have fairly low temperature interaction. Okay, we never exceed, at least in the outer part, 100 degrees Celsius or so. So fairly low temperature, and that kind of persists over time. The temperatures are very homogeneous, but the interaction takes place over a very long time. So we'd expect aqueous alteration to have been pervasive. Now you can see this from the chemistry. So this is one of the ternary diagrams again, showing, so with iron oxides on this apex, magnesium here, and silicon and aluminum here. And others can chime in who know more about me than this, but essentially the carbonaceous chondrite meteorites, which are thought to be potentially some of the building blocks that Ceres and other ocean worlds formed with, tend to have a mineralogy that's more iron-rich if they're less aqueously altered, or thought to be less aqueously altered. And then the mineralogy tends to have more magnesium and silicon. And then Ceres surface plots kind of in this area of the plot, suggesting, again, that there's been more aqueous alteration than in these meteorites. So what Julie's been doing is building these geochemical model, reacting essentially the kind of chondrite meteorite with fluids bearing a little bit of carbon and nitrogen, and looked at what the resulting mineral assemblages look like as a function here of water to rock ratio. So this is 100 parts of water per part of rock, and here it's 10 parts of rock for 1 part of water. And you can see how the assemblages vary. But she's able to reproduce pretty well what's been seen at the surface. So these magnesium serpentines, some saponite, and some of the components that could be darkening the surface, such as magnetite, as well as carbonates that are being observed on the surface of Ceres, like magnesite. Okay, so again, it's these are equilibrium models, and as Tucker mentioned this morning, this is where an environment would tend to go. It doesn't necessarily get there, but in this case, it looks like Ceres, at least qualitatively, has a composition that's akin to equilibrium products. Specifically, the match is better at slightly higher water-to-rock ratios, and once again, that's an indicator that aqueous alteration has been pervasive and has lasted a long time, and each parcel of rock has seen a lot of water. Okay, the other work that she's done is taking the composition of the fluid in equilibrium with that rock and then freeze it down. Okay, so today's Ceres is most likely a relict ocean world. Ceres is probably too small, didn't have access to tidal heat sources, not orbiting any planets, just orbiting the sun. And so it's very likely that over time it's cooled down to the point where the entire hydrosphere has frozen. And so that must have affected the chemistry of the fluid. And so what she's been doing is taking the fluid composition, starting it at the freezing point here for water ice, and looked at how the composition might have evolved as the temperature decreased in the ice shell. So the first thing that precipitates is water ice, of course, and then the fluid been rich in sodium and some carbon nitrogen compounds, as well as chlorine, at low pressure would first start precipitating sodium carbonates, and eventually when you hit minus 20 Celsius or so, chlorides would start forming, and eventually what's left in solution is the methane, and her models tend to form methane clathrates. Now at higher pressure, so this is more mid or to bottom of the ocean once the ice shell has frozen, clathrates tend to be the dominant compound in her models, suggesting that perhaps you would have an accumulation of salts a little bit closer to the surface, and with the deep part of that layer being richer in clathrates. Now that's also consistent with some of the observations, not of the surface composition, but of the surface rheology, or the strength. So as Paul mentioned, the outer layer of Ceres is quite low density but quite strong, and you can't explain this just with a mixture of ice, rock, and salts. You have to invoke the clathrates that are pretty strong and pretty low density. Now that we see evidence for that salty, briny liquid getting to the surface. So this feature here is what's been interpreted as a cryovolcano on the surface of Ceres. It's a few kilometers in height and about 30 kilometers in diameter. The flanks of the volcano are covered with this sodium carbonate material. And it looks like we're seeing evidence for recent activity of remnant fluids getting squeezed up to the surface. So perhaps one of the last pockets of liquid in Ceres' outer layer freezing and squeezing out some materials. Okay, now this is something new for those of you who are familiar with Ceres. I actually learned about this today. So this is a map of Ceres in visible wavelength, and this is a compositional map showing the abundance of hydrated sodium carbonate at the surface. And specifically two areas flash here. This first area is the Okator crater that Paul was talking about, where we're seeing a lot of this bright material, which also seems like a very recent effusion of material from Ceres interior. But the second spot here in another crater called Haulani, which looks pretty bright too, seems to be rich in sodium carbonate as well. And now it's not, it's actually hydrated sodium carbonate, which apparently would seem to have to form in fairly warm liquid. So the previous evidence we had for sodium carbonates was the dehydrated form. And here I might get speculative. I would think that you would lose the water of hydration, for example, at the surface by space weathering processes and so on. But what Julie is arguing here is that to form that still in a hydrated form, the fluids would have to be pretty warm, and the effusion would have to be very recent. And so I think she's interpreting this as evidence for very recent fluids close to or perhaps even above the freezing point for pure water. Okay, So Paul mentioned that there are different organics at the surface. So I should mention that the surface is pretty dark, right? Reflects less than 10% of the light, and is very likely part of this is very likely some carbonaceous material, but probably amorphous carbon. Now the organics that we're seeing that's next to this old Ernetat crater are aliphatics, it seems mostly, and so there have been questions about how do you form these, and she refers to the work of Simone Marchi here at Squarey in Boulder, who have attempted to look at organic synthesis driven by heating from an impact, and they can't really make it happen. Presumably these organics formed before any impacts happen and then were excavated from the outer crust. So I don't think there is a good explanation as to how these organics form. One of the ways I would think about is on the way to reducing oxidized carbon. You kind of stop at metastable compounds just because the kinetics are too slow, and perhaps that an impact can excavate this afterwards. The organics are not super well characterized yet. In the infrared, we're just seeing evidence for carbon-carbon bonds, but we don't know yet about any heteroatoms or any other features that could help ascertain their origin. Okay, so Ceres is telling us, it's kind of a window into the water rock chemistry of other ocean worlds. It's probably the world for which we have the best handle on the rock chemistry, and so as such, it's a pretty useful tool to interpret what we might be seeing elsewhere at Europa and Enceladus, and usually even goes into other worlds. For example, the existence of the clathrates has been postulated for objects such as Titan and Pluto. Yeah, so that's kind of the end of it. But if you have any questions, we'll be happy to take them. Thank you.
Thank you so much, Paul and Mark, for filling in. Questions for the tag team? Oh yeah, great. Thank you. It's a question for Paul, and I apologize if I missed this, but I'm confused about the interior differentiation state of Ceres, because you said it was partially differentiated, but you also mentioned a core with a reasonable porosity. So what do you actually mean by partially differentiated, and does it actually have a core, do we think?
We need the geophysical experts here, and I know Bill can chime in on that. If I said core, I probably should have said possible core. I don't know what the current thinking is on that. Bill probably knows because he keeps up on the literature more than I do on that.
It's just basically the gravity and topography of Ceres requires that the thin, in a sense, outer layer of Ceres be much lower density than the bulk body. At the same time, just like Paul was saying, the lack of crater relaxation, which was predicted, shows that it can't be pure ice that, let's say, is just dirty on the surface. So that's why Mark and Paul have both been invoking salts and clathrates, basically, because obviously salts are stiff, and clathrate turns out to be very stiff as well, water-ice clathrate. That's on the outside. Then the rest of it is just basically most of Ceres. It's a little denser than the main thing, like 2.4. And the idea that it's porous is that if you want to make something of that density meteoritically with cosmic iron, you're going to have porosity.
I don't recall there's any firm data on whether there is any kind of core.
Well, I'm calling the whole entire interior underneath this. Usually, all the geophysical models can be explained with a two-layer scenario in terms of composition.
They don't require any core that I'm aware of.
All right.
That was a misspeak.
Question for Kevin here.
Thanks, Paul and Mark. Nice work. One quick thing and one longer thing. On the organics, I saw you had the single bond carbon-nitrogen listed as not observed. What about the nitrile bond, the triple bond? Because that's the one that spectroscopically jumps out at you. Has there not been any detection of nitriles?
Not that I know of. There may be new developments among the team.
But so far,
I know about it.
Okay.
I'm not aware of anything myself. So.
And then the second thing is I haven't kept up with the literature on this, but initially, wasn't there a little bit of special pleading involved in invoking the aluminum-26 to keep Ceres hot? We had to say something about enhancing the aluminum-26 ratio in the early nebula and nearby supernova or something. Where has that gone, or has everybody just kind of accepted a higher level of aluminum-26 throughout the solar system? Because if you invoke it for Ceres, you gotta do it everywhere, right?
Sure. It's been invoked before then, though, right?
Well, but nothing had catalyzed it the way
So
Ceres did.
Kevin, so the old models, the pre-dawn models, you would see little graphs, and like Julie or Christophe Sautin would make, you'd have like this thick ice layer, it looked like Ganymede or Pluto, that usually invoked aluminum-26. But the dawn data say that really there's a much less separation. So it had to form later with less live aluminum-26 because it's not fully separated. There's been obviously.
I'm sorry, dig into that. It had to form.
It had to form late enough that the amount of aluminum-26 incorporated was not as large as it could have been. Right? It burns out every 720 million thousand years, the half-life.
So I think I get you. I'll follow up with you.
Yeah. I mean,
Okay. Just for those of you who are not aware, so aluminum-26 is thought to be a short-lived radionuclide heat source to have fueled some early activity on Ceres. I would just add to this that indeed the dawn data have revealed that Ceres is not as differentiated as we thought, and this idea with the models of this muddy convection in the interior allow for a much longer-lived internal activity that you'd get otherwise if you just have a pure ice shell and a pure rocky core. So that really helps homogenize temperatures in the interior, tap the heat from the core, the radioactivity from the core, and so you're able to not differentiate yet have a lot of aqueous activity.